How's it going, everyone? Today we're going to be looking at the very last problem of our practice test for Chapter 10 in AP Calculus. This is question 14, where we're first starting by finding the radius of convergence for the series x to the n to the n over n factorial. Well, I'm looking at this series and, I don't have much hope for this, but we really should be checking to see if this is a geometric series. But this is probably not going to be a geometric series because we can see the factorial already, and the factorial is a big no-no. And also there's this n to the n, and when we have an n that no longer appears as the exponent, this is a warning sign that we're not looking at a geometric series. But let's pretend we didn't notice all that. We're going to put together all of our terms, or at least the first 4 terms anyways. And yeah, I don't think this is a geometric series. There's not the mechanism to get from one term to the next is definitely not multiplication. So what do we do if we have a series that's not geometric? That's right, we're going to use the ratio test. So let's take a look at the ratio. The limit of the n plus 1th term over the nth term has to be less than 1 if you want that series to converge. Take the general term and rewrite it so that all of the n's have been replaced with n plus 1. Be very careful with algebra. If you don't put things in parentheses, things won't, well, obviously they won't turn out correctly. So be careful with your algebra. Multiply that by the reciprocal of the general term, and you got yourself the good start to the ratio test. Like every other for every other ratio test, I like to group things together. So you'll notice we have x to the n plus 1 and x to the n. I'm going to put those together on their own fraction bar. We also have the factorial stuff, n plus 1 factorial and n factorial. And lastly, we have the exponential stuff, n plus 1 to the n plus 1 and n to the n. Kind of nervous about that n plus 1 to the n plus 1 power over n to the n. Not quite sure how that's going to work out, but let's take a look. Now that I've grouped everything together, let's take a look at canceling things out. Now you wouldn't necessarily need to write this step, but as far as canceling goes, let's cancel with this marker. If we cancel, we can cancel x to the n with an x to the n. That's going to leave me with an x to the n, with just an x over there. Simplifying the factorial business, it looks like I can actually cancel the n factorials. So let's cancel the n factorials while we're at it. Then let's simplify the exponential stuff. And when I simplify these factorial or the exponential things, I don't actually get to cancel anything from the factorial side, but I do have the advantage of being able to cancel out the n plus 1. So that works out nicely, and we can see the only things that are going to be left are going to be the x and the n plus 1 to the n and n to the n. Now the x, I can, the x right over here, I'm going to highlight this. This really doesn't have an n anymore. So that x I can take out of the absolute, or out of the limit, as long as I maintain those absolute values. N plus 1 to the n and n to the n have the same power, so I can group those together and give them both the power of n. And now I'm left with this limit, n plus 1 over n to the nth power. And to do that, we're going to do that kind of on the side. So here on the side, we're going to work on that limit n plus 1 to the nth over n. Let's try and figure that part out. Now reaching back a couple of chapters, if we see n something to the nth power as is exponential, this is actually a disguised form of our indeterminate form. This is an indeterminate form because it looks as like we're going to get infinity to the infinity power. So the correct way to deal with this, we'll make a function called y, and we'll set it equal to n plus 1 over n to the nth power. And then we'll take a natural log of both sides. And the reason we're taking the natural log of both sides is so we can take that n out of the exponent and bring it in front of the natural log. Okay, so now we have this natural log of y equals n multiplied by the natural log of n plus 1 over n. We're going to simplify this by dividing. Instead of multiplying by n, we're going to divide the natural log by 1 over n. I just noticed that that last line wasn't exactly correct, so here we have it. We're going to apply a limit to both sides. And now we have the natural log of, as n goes to infinity, this is going to be the natural log of 1, which is 0, over 1 over n as n goes to infinity, which is going to go to 0 as well. So this is 0 over 0, a indeterminate form. So we're going to divide both sides. We're going to take the derivative of the numerator and then the derivative of the denominator. It's kind of a messy derivative, but 1 over 1 plus 1 over n is how we take the derivative of any natural log. And then we multiply by the derivative of 1 plus 1 over n, which is negative 1 over n squared. The denominator is still negative 1 over n squared from that derivative. And I think you see that we have the opportunity here to do some canceling. So we're going to take it, this guy and this guy. Those are going to cancel out. And that's going to give us that the limit of the natural log of y is going to be the limit of 1 over 1 plus n. And as n goes to infinity, 1 over n goes to 0. So the limit of the natural log of y is just 1. Now we're just going to exponentiate, and the limit of y is e, which is to say that the limit of n plus 1 over n to the nth power is just e. Now, let's go back to our main problem. We have the limit as n approaches infinity of n plus 1 over n to the nth power. We just discovered that the limit is e, so that we get the absolute value of x multiplied by e must be less than 1 for the ratio test to be convergent. Now, if I take that and I turn it into the x minus the center is less than the ratio, less than the radius, that is, I get that the radius of convergence is 1 over e, which completes part A of this problem. Now, that was a very difficult limit for us to work on. So, yeah, this was a tough one. Okay, let's take a look at the next problem in this number 14, and it says to use the first 3 terms of the series to approximate f of negative 1/3. Now, negative 1/3 is in the interval of convergence, so you may want to check that, but it is. So we can just use the series, the first 3 terms of the series as it says here, and if we substitute negative 1/3, we'll get an approximation for f. So from part A, these are the first 3 terms of the series. And this is written as a series. So we're just going to truncate this series to 3 terms now. And when we truncate, we turn this from an exactly equal to an approximate. So f of x is approximately equal to these 3 terms. Now there's not a whole lot more to this. We're just going to substitute negative 1/3. And then we're going to do some algebra. And we get that f of negative 1/3 is about equal to 5 over 18. So that completes part B, and we can move on to part C. Let's show that this approximation differs from f of negative 1/3 by less than 1/4. Now, whether you recognize it or not, this is asking for the error of our estimation. And as a refresher, our error could either be the Lagrange error for any series. We're going to use that specifically for series that do not alternate, and the alternating series error, which is obviously only used for alternating series. So let's take a look at our series that we got from letter B, and we notice that we have positive term followed by a negative term followed by a positive term followed by a negative term. So this is an alternating series. And you should be doing your happy dance here, because the alternating series error is a lot easier to compute than the Lagrange series error. Now, since we used 3 terms to approximate f of negative 1/3, well, then the error should be less than the 4th term. In other words, the error should be less than the absolute value of negative 1/3 to the 4th multiplied by 4 to the 4th divided by 4 factorial. And you just have to compute that. Now, since the question asks that the approximation differs from f of negative 1/3, we're going to re-express error as f of negative 1/3 minus the answer that we got from letter B. So f of negative 1/3 minus 5/18. Don't let that fool you. That's just the same thing as error. So error is less than, and then we simplify a little bit to get 1/81 multiplied by 2/56/24. Remember, don't get nervous here. This is not something you're going to evaluate. That's just, this right here just says error. It's not a math problem. So simplified, we have that 32 over 243 is the bound for the error using the alternating series error. And since 32 over 243 is less than 1/4, then my error is less than 1/4 as well. So we've just shown that the approximation 5/18 differs from f of negative 1/3 by less than 1/4. And that's it. That's our entire practice test. Good luck on your Chapter 10 test, and we'll see you next time when we look at Chapter 11. Have a good one.